In this video, we are going to discuss the site location attributes for developing the ELF method. But before we do that, I do want to make one correction from the previous video. So I'm going to scroll back to the notes from the previous video. Let's see. I had a incorrect, let's see, where is it? I had an incorrect figure reference. There we go. Yeah. So I said figure 416 here. This should be figure 417. If you're looking in the book, you probably would have figured that out by now. Okay, so let's go on and talk about the site location attribute of the ELF method. So regional seismicity is an important attribute of earthquake loads. Instead of writing out earthquake, I'm gonna say EQ loads. Okay, so take a look at, I'm gonna say see figure 418 of the text. This is the correct figure this time. So figure 418 in the textbook, which, let's see what page that's on. That's on page 113. Shows a map of the U.S. This is an example of a seismic hazard map of the United States. And if you see, it's color-coded with the highest level of seismic hazard being kind of a pink color. And if you're taking a look at this in the textbook, you see all of the western United States, California area is very seismically active. But if you look closely to the Memphis, Tennessee area, we are also very seismically active. We have the New Madrid seismic fault in the Arkansas, Illinois area that if it ruptured, it would cause a major seismic event in this part of the country. So this is why we care about earthquake loading so much in the Memphis area. Okay, so that's just a little bit about that. So how do we go about investigating the site location? Well, the first thing you want to do is determine what's called the soil site class. Okay, and this is going to be table 4.4 of the text and table 20.3-1 of ASCE 716. So, you can use the text for this for sure, but you need to also get used to using ASCE 716 because, again, that's what you're going to have access to on a quiz in the midterm exam, okay? So if we take a look at either of these tables, whether it's in the text or ASCE 716, what do we have? Well, we have several different criteria in these tables. If you look at the top row, we have shear wave velocity, field standard penetration number, and undrained shear strength. And then the site class is the leftmost column, with the next column giving a soil description of the site class. So for example, site class A is considered hard rock, and it has a shear wave velocity of more than 5,000 feet per second. So make a note here, we'll make a note here, an FPS is feet per second. So of course it's a velocity term. That's why it's called shear wave velocity. And then the field standard penetration number and undrained shear strength are not applicable. Those are geotechnical values that we'll study more in a soil mechanics course. So you see the definition of each of these soil site classes. In the Memphis area, we have a lot of soil site class D. So in the Memphis area, we have a lot of stiff soil with a shear wave velocity between 600 and 1,200 feet per second, a field standard penetration number between 15 and 50, and an undrained shear strength between 1,000 and 2,000 PSF, okay? Now, there are parts in the Shelby County area that's site class C and also site class E, but for the most part, we have site class D in the Memphis Shelby County area. Okay, so let's talk about some of these values here. The shear wave velocity, so shear wave velocity field standard penetration number and undrained shear strength are determined from geotechnical field and lab testing of the site's soil. So in terms of what these numbers are, we're not really going to get into the theory behind shear wave velocity, penetration number, or undrained shear strength in this class, but we will talk about it extensively in soil mechanics, which most civil engineering students take first semester junior year. So most of you will take that next semester. For our purposes in structural engineering is we're just going to use these values, okay? So we're going to assume that the geotechnical engineer has provided us these values to use for our purposes, okay? So for conflicting values, okay? So if you have conflicting values, spell that correctly. For conflicting values, use the site class with softer soil. Okay, so do this. Let's look at table 4.4 in the text or table 20.3-1 of ASCE 7. And let's say, for example, let's say that you have a shear wave velocity of 2,400, okay? 2,400 feet per second is your shear wave velocity. And let's say that you also have an undrained shear strength of, let's say, 1,900 PSF. So the shear wave velocity of 2,400 feet per second would indicate what site class? Pause the video. I'm about to tell you the answer. 2,400 feet per second shear wave velocity would indicate site class C, very dense soil and soft rock, okay? But your undrained shear strength, if you had an undrained shear strength of 1,900 PSF, that would indicate a site class D, stiff soil. So which one do you use if you have conflicting values? Well, you use the softer soil, which would be site class D, stiff soil. So site class A is the hardest, and then all the way down to E and F are the softest. Okay, so keep that in mind, okay? The next thing you want to do after you determine the soil site class, we'll put another bullet point here, is determine the maximum considered earthquake geometric mean. And we abbreviate this as MCE sub R, okay? And this is a peak ground acceleration. And it corresponds to, I'm going to say corresponding to a period of t equals 0.2 seconds and another value corresponding to a period of 1 second. Okay? Now, a lot of words here, okay? What you're determining is an acceleration value actually two of them, two acceleration values that correspond, one that corresponds with a period of 0.2 seconds, the other 1 second, okay? And you get these, we're going to say obtain from figures 22-1 through 22-8 of ASCE 716, okay? So there's maps. These figures are maps. So go ahead and open up your ASCE 716 and go to these figures. You'll see they're maps that you will obtain these acceleration values from. So you got to look at the title of the figure at the bottom of the page and make sure you're looking at the correct figures that you need to be looking at for these values, okay? So these are based on a soil site class B, okay? So what you got to do is you got to, keep that in mind, and we're going to make some adjustments to, transform it into whatever soil site class you have if you don't have B, for example, okay? So these are labeled, these two acceleration values are labeled as S sub S for t equals 0.2 seconds and S sub 1 for t equals 1.0 seconds. Okay, so here's what's a little confusing. SS is the peak ground acceleration corresponding to a period of 0.2 seconds, and S1 is the label for the peak ground acceleration corresponding to a period of 1 second. So this is just how they're labeled. So SS and S1 are acceleration values, and they're usually given as a decimal of G. Okay, so SS and S1 are typically a decimal of G. So for example, I say for example, e.g., if SS equals 0.3, that means SS equals 0.3 Gs. Now, what's a G? A G is 32.2, right? 32.2 feet per second squared. So SS would be equal to 0.3 times 32.2 is 9.66 feet per second squared. So what does this really mean? This is really like a horizontal acceleration that you calculate based on a decimal of G. Now, really, you just use this. You're going to end up using 0.3 because all of our later procedures are based on you just using the percentage. So you don't actually have to calculate this, value times G every single time. Actually, you rarely ever have to calculate that, okay? So the next thing we do is we're going to say the next bullet point, obtain site modification coefficients FA and F sub V from tables 11.4-1 and 11.4-2 of ASCE 716. So again, you need to have your ASCE 7 out, and we're in the provisions, by the way. We're in the provisions. And you go to these tables and you obtain these site modification coefficients, okay? And that way you can adjust for whatever site class you actually have. So you got to enter those tables correctly, okay? And then what we do is we compute the design accelerations as SDS equals 2/3 FA SS, and then SD1 is 2/3 FV times S1. Okay, and you can take a look at example 4.9 in the text. Okay, see example 4.9 in the text for this part of the procedure. Okay, and again, you're gonna have to read the text. I mean, a lot of this information is kind of it's kind of dense information, so you need to be reading along in the text and following along with ASCE 7 as well. So that concludes this video, and then we're going to have another video that describes the structural aspects.